These are the notes for AP Calculus on the topic of the intermediate value theorem. So, intermediate, just think about what that word means. It means in between two things. So that's what it means in this theorem as well. So with any theorem in math, there's always an if statement. Something is true, then, and the then part of the statement. Then this must also be true. So the if statement in the intermediate value theorem is if the function f is continuous on a closed interval from a to b. And what it means by a closed interval is that the endpoints are included. And you can see that they're included because of the brackets. As opposed to an open interval would be with parentheses, where the endpoints are not included. And sometimes you have an interval that's one end is open and one end is closed. But in this case, it has to be a closed interval for the intermediate value theorem to apply. Then what it guarantees is that f takes on every value between f of a and f of b on the interval from a to b. So to understand this better, let's see what this looks like graphically. So a and b just represent some x-coordinates. In this case, here's a, here's b. And let's take a look at this graph. Is this function continuous on that interval from a to b? Yes, it is. There are no holes, no vertical asymptotes, no breaks in the function. It's all connected. So because it's continuous on the interval, we can apply the intermediate value theorem. And what it tells us is f of a and f of b, those are just the y values, right? So here's f of a, the y coordinate at this point. And here's f of b, the y coordinate at this point. So it's saying that the function has to equal every one of the y values between these two y values at least one time. Now, that's one way the theorem is worded. This is the same theorem, just worded in a slightly more specific way. Again, it has the same condition if f is continuous on a closed interval from a to b. But this time, it says, and k is between f of a and f of b. So k just represents any y coordinate that's between these two y values, f of a and f of b. Then what it says is then there is at least one c in a to b. Notice this is an open interval because c can't be at the endpoints. It has to be somewhere in between here, such that f of c equals k. So that when you plug that specific x value c into the function, it gives you the specific y value k that's between f of a and f of b. So let's see how this looks in some example problems. A lot of times these problems will be in tables of values. So this one says the table below shows several measurements of the velocity of a bicycle riding on a straight road. V of t is continuous on the interval 0 to 20. So for our whole table there, it's continuous. If it didn't tell you that, then we could not apply the intermediate value theorem at all. But since it does, we can do that. And notice the first row represents the time in seconds, and the second row represents the velocity at that time in meters per second. So it says from 0 to 20, if t is between 0 and 20, must there be a time t when the velocity equals 2.5? And then justify your answer. Well, we know it's continuous. The only question is 2.5, this y value, in between the y values on these different intervals? So let's look and see. Is 2.5 between 3.3 and 4.2? No, it's not. So the intermediate value theorem would not guarantee that the function would have to equal 2.5 on the interval from 0 to 5. So to the next one. Is 2.5 between 4.2 and 2.7? No, it's not. So we can't apply it there either. Is 2.5 between 2.7 and 2.3? Yes, it is. So we can apply on that one. And that's all we need. Must there be a time? So there must be because of this interval right here. So your answer would be yes. There's actually another interval we also could have used. Because notice 2.5 is also between 2.3 and 3.8. But it's not between 3.8 and 4.6. So we also could have used this interval here. It really doesn't matter. In this case, there's two possibilities. So now let's justify our answer to be yes, since first we have to mention it's continuous. And it's continuous on 0 to 20. Here the specific interval we're talking about is from 7 to 9. So since v of t is continuous on the interval from 7 to 9. And we also have to state mathematically that this 2.5 is between these two y coordinates. So the easiest way to do that is to start with either one. I'm going to start with v of 7. V of 7, the y coordinate there. This time that's greater than 2.3, and that's greater than 2.5, so that would be greater than you put 2.5 in the middle, we're going to use a compound inequality here, and then 2.5 is greater than 2.3, which is our v of 9. So that's showing us that 2.5 is between the two y coordinates. And then the last thing you can mention is to mention the theorem that you're using by the, and then intermediate value theorem you can abbreviate as IVT. Then it says from 0 to 20 must be a time t when the velocity equals 5, justify your answer. So it's up, does the velocity have to, is 5 between 3.3 and 4.2? No. Is 5 between 4.2 and 2.7? No. Is 5 between 2.7 and 2.3? No. Is 5 between 2.3 and 3.8? No. Is 5 between 3.8 and 4.6? No. So the answer is no. 5 is not between any of those, so it doesn't have to equal 5. Doesn't mean it couldn't, but it says must there be a time, so there doesn't have to be a time. And the way you justify when the answer is no is you could say since there are no known values of v of t, our velocity, that 5 is between. There might be some values of 5 is between, none that we know of. That's why I added the word known here, because we don't know what's happening on all these other times other than the ones we're given. All right, then the last part's worded a little differently. It says, what's the least number of times where the velocity is exactly 4 meters per second? So let's look at each of these subintervals here and see if it has to equal 4. So is 4 between 3.3 and 4.2? Yes, it is. So there's one time between 0 and 5 where the velocity would have to equal 4. How about the next one? 4.2 and 2.7? Yes, 4 is between those as well. So there's a second interval between 5 and 7 where the velocity would have to equal 4. Is 4 between 2.7 and 2.3? No. Is 4 between 2.3 and 3.8? No. Is 4 between 3.8 and 4.6? Yes. So there's a third time between, on the interval from 14 to 20 that the velocity has to equal 4. So your answer here would be that v of t equals 4 at least 3 times. And then the way you could justify that would be since, and you could say v of t is continuous on each of these smaller intervals, or an easy way of saying that is just look at the whole interval and cover the whole thing. So since v of t is continuous on, just going to use the big interval, 0 to 20, and v of 0, notice this one, 3.3 is less than 4.2 and 4. They'd say less than, put 4 in the middle, which is less than v of 5. The next one would be from 5 to 7, so v of 5, but this time v of 5 is the greatest of the two. So the v of 5, which is 4.2, is greater than 4, and 4 is greater than v of 7. And the last interval, v of 14, that's the smaller of the values, that's less than 4, which is less than v of 20. We'll just add by an intermediate value there, which can abbreviate as IDT. Okay, let's look at the next example problem. This one's just a table organized vertically here. It says the number of people waiting in line at the try and save on the day after Thanksgiving is modeled by a continuous function L of t. So it tells you it's continuous from 0 to 7. Values of L of t at various times t are shown in the table. And then the question asks you from the interval from when t is between 0 and 7, what's the fewest number of times at which L of t equals 50? Give a reason for your answer. So let's take a look. We know it's continuous, so we can apply the intermediate value theorem. We just have to see if 50 is between the y values or not. Is 50 between 25 and 37? No. Is 50 between 37 and 84? Yes, it is. So it would have to equal 50 at least once between on the interval from 1 to 3. Is 50 between 84 and 97? No. Is 50 between 97 and 121? No, it's 50 between 121 and 46, yes. So your answer here would be twice. There's two separate intervals where the line, number of people waiting in line, which L of t represents, is equal to 50. So L of t equals 50 at least 2 times, since, and you could say it's continuous on each of these intervals separately, or we could just say since d of t is continuous on interval from 0 to 7. Just writing this instead of inequality notation in interval notation. And we know that, not d of t, sorry, L of t. D of t was the last one. And L of 1, since that's the smaller of the values, is less than 50, which is less than L of 3. And L of 5 L of 5 is, that's the greater the value, so that's greater than 50, and 50 is greater than L of 7. And then just mention the theorem by the intermediate value of by dt. Now let's take a look at one that's a little bit different. It says the functions f and g are continuous for all real numbers. Then the function h is given by this, h of x equals g of f of x minus 3. So, g is just made up of a composite of 2 continuous functions. Sorry, h is made up of a composite of 2 continuous functions. So we can say h is continuous on all real numbers again, or you can just say it from negative to negative. Then it says, must there be a value r from, or r is between 1 and 3, such that h of r equals negative 2. And explain your reasoning is just another way of saying justify your answer. So, notice the difference is we don't have a table for h. We just have a table for f and g. So what we're concerned with is negative 2 between the y values at these endpoints, 1 and 3. So let's check and see if it is or not. So we can say h of 1 equals g of f of 1 minus 3. F of 1 is 2, using the table. So g of 2 minus 3, g of 2, using the table, is 9. Gives you 6. Now let's find the y value at the other endpoint of our interval 3. So h of 3 equals g of f of 3 minus 3. F of 3, let's see, is 4. G of 4 is negative 1. Negative 1 minus 3 is negative 1. So let's take a look. Is negative 2 between 6 and negative 4? Yes, it is. It is between there. So that means that there must be a time when h of r equals negative 2 on the interval by the intermediate value there. So we can say yes. This would be a yes or no question. Since first h is continuous on interval from 1 to 3. It's continuous everywhere, from negative infinity to infinity. It's continuous on 1 to 3 as well. And h of 1, which was 6, that's greater than negative 2. Negative 2 is greater than h of 3, which is negative 4. And then just add by the intermediate value. Now let's take a look at a similar question. Must there be a value r where r is between 2 and 4 such that h of r equals 1? So let's see, h of r equals 1. So we have to find h of 2 and h of 4 this time. So h of 2 would equal g is in this function right here, g of f of 2 minus 3. F of 2 is 3. So g of 3 minus 3. G of 3 is 10. Minus 3 gives you 7. And now let's find h of 4, the other input interval. H of 4 would be g of f of 4 minus 3. F of 4 is 1, so that becomes g of 1 minus 3. G of 1 is 6 minus 3 gives you 3. So let's see, does h of r have to equal 1 on this interval? Well, is 1 between 7 and 3? No, it is not. So it's not between 7 and 3. So this time it does not have to equal 1. And then say no, since 1 is not between h of 2 and h of 4. All right, let's take a look at some multiple choice type of questions dealing with the intermediate value theorem. So in this one, we're given the function f is continuous on the closed interval -1 to 2. All right, so that's important to know that we could use the intermediate value theorem potentially since it's continuous. And some values of f are shown in the table. The equation f of x equals 5 halves must have at least 2 solutions in the interval 0 to 2 if k equals which of these? So notice the slight difference. This says -1 to 2, this says 0 to 2. So that means what happens here at -1 to 4 is not an interval from 0 to 2. So in this case, that's irrelevant for our problem. It's not an interval we're looking at. So be careful and see if the intervals are the same. Sometimes they might be, but not in this case. So the easiest way I think to kind of figure out what's going to happen here is if we graph it. So here we've got the point. This is the x and this is the y coordinate. 0, 6 we know goes through. So this goes a little bit better. So, one point we know it has to go through is 0, 6. Right up here. Oops. Right up here. 0, 6. And it also goes to the point 2, 3. So what it's saying is, which of these potential values for k, which is the y coordinate 1, would cause this f of x, which is like y, equals 5 halves is like 2.5 to have 2 solutions. In other words, the function equals 2.5 at least twice. So let's graph y equals 2.5. That's just a horizontal line. Right there. So in order for this to have 2 solutions, it has to cross this line at least twice. This function, which is f of x, has to have y coordinate of 2.5 at least twice. So let's look at these potential y values. Let's start with the first choice, a is 4. So if k equals 4, 1, 2, 3, 4, would the function on the interval 0 to 2 have to cross this line twice? No. All we know it's continuous, so it doesn't even have to cross it once if you go like that. So that's not going to make it have 2 solutions. It may have 1. Let's look at 7 halves, which is 3.5. Right there? Nope. It wouldn't have to cross it again. Let's look at this choice C is 3. Nope. It wouldn't even have to cross it there. It could just go like this. Never cross that line. But what about 5 halves, which is 2.5? It goes right on the line. Would it have to have 2 solutions? Take a look. No, because you could draw it where it just barely touches that and only has 1 solution. But if you look at the last choice at 2, if the y coordinate is 2, then you can see, oh, okay, well, in order to be continuous and go through that point, it has to go down here, and then it has to come up here. So it would have to cross this line twice, at least. And we're really using the intermediate value theorem, because if it was 2, 2.5 would be between 6 and 2, and 2.5 would also be between 2 and 3. So we're applying the intermediate value theorem twice on 2 different notes. Let's take a look at one last one. It says the function g is continuous on an interval from -3 to 2. If g of -3 is 5 and the inverse of g of -1 is 2, which of the following statements could be false? All right, so let's first translate this inverse. This means that if you plug a -1 into the inverse, you get 2 for the y coordinate. So -1, 2 is on the point on the graph of the inverse of g. And remember how inverse functions work. They reverse all the x and y coordinates of the original function. So that means that 2, -1 is on the original function g. And the way we can write that over here is g of 2 equals -1. And now let's take a look at the question. Now we're looking for the one that could be false, remember. So that means all these have to be true except for one that might be false. So it says there exists a c where -3, the c is between -3 and 2, so on this interval where g is continuous, such that g of c equals 1. Well, let's take a look. Is 1 between 5 and -2? Yes, it is, and the function is continuous, so this one would have to be true, and then by the intermediate value theorem. There exists a c where c is between -3 and 2, such that g of c equals 3. Is 3 between 5 and -1? Yes, it is. So this one's also true by the intermediate value theorem. The function g has at least one 0 on the closed interval -3 to 2. Well, at least one 0 means that g of c equals 0 at least one time on this interval from -3 to 2. So is 0 between -5 and -1? Yes, it is. So this one's also true by the intermediate value theorem. We look at the next one. There exists a c where c is between -3 and 2, so that's just g of c equals -2. Is -2 between 5 and -1? No, it is not. So because of that, this one doesn't have to be true, so this is the one that could be false. Because this is not between g of -3 and g of 2, unlike the other ones. And let's look at the very last one. That must mean this one has to be true, but let's see why. This one involves a limit. It says the general limit as x approaches -2 of g of x exists. The easiest way to see this one is graphically, probably. So we sketch a little graph here. So -3, 5, and 2, -1. So if we plot those 2 points, notice we know it's continuous. We don't know what it looks like. It does look something like this. No, something continuous. And it's saying the limit as x approaches -2 exists. So here's where I drew -2. So look, does the general limit exist? Well, is it approaching the same thing on the left and the right? Yes, it is. So this one must be true. And notice this would be true not just of -2, but of any x value that's between the endpoints, not including the endpoints. So between -3 and 2, because it's all continuous, when it's continuous, the left and right limits are always equal. However, at these endpoints, it wouldn't have to be continuous there because we don't know what's happening after those points. And that concludes the notes for AP Calculus on the topic of the intermediate value.